Ray Weidekamp is the CEO of Polyspectra, one of our Prime Movers Lab portfolio investments. And Ray got his PhD from Caltech and fortuitously came across the invention that he'll describe a little bit later today. But first, he's going to give an overview of additive manufacturing, part of the 3D printing world that's applied to particular segments of manufacturing that happen to be quite large and important. And for those of you that are listening, we'll have Ray kind of share with us about the sector for about 15 minutes and then about the company for about the same amount of time. And then we'll have 20, 25 minutes for open Q&A. And when it gets to that, I'll kind of call on people and moderate. If you know how to raise your hand on the system, go ahead and do that. If you just need a text or email me to let me know that you want to ask a question, that's fine too. But I'm going to turn it over to Ray, who is much better equipped to speak on this subject, and I'm sure we'll all enjoy it. So thanks, Ray.
Yeah, thanks for the invitation. Yeah, hopefully everybody can hear me okay and see the slides. As Deacon mentioned, I'm going to do a brief overview first, then I'll tell you a little bit more about the piece of this puzzle that Polyspectra is trying to solve, and we'll leave plenty of time for questions. So very high level in terms of market. Last year, additive manufacturing was approximately $10 billion market. Has been, growing around 25% year over year for the last 5 years. And we'll see where things go in the future. About half of this is in services, and the other half is in, the sort of additive manufacturing products themselves. This is an older chart, but on the right-hand side, you can kind of see that breakdown. So this is from 2014. This is the ratio of sort of services to products has stayed pretty consistent, but you can see that I forget which one, purple or blue, is services or products. But either way, it's about 50-50 for almost all years, and that stayed true. And then, in terms of sort of sectors that this is applied to, you can see that the sort of auto, aero, and industrial machines combined is almost half of the entire additive manufacturing market breakdown. There's a solid chunk in medical and sort of growing applications in consumer products and electronics. Anyways, this is a super high level breakdown. So what I wanted to do next is I'll probably spend the most, in terms of the overview, I'll try to spend kind of the most time here because I think it's fun and I feel like I can do a decent job of explaining all of this. So I guess, I for the purposes of this webinar, I'm going to use kind of 3D printing and additive manufacturing interchangeably. I think, there's, the way Dakin described it was like, additive is kind of applying 3D printing to industrial manufacturing problems. The problem is that word gets sort of bastardized, and like they're actually, I think one of the points that I'll try to get across in this talk is there are actually very, 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 very few things that like would truly qualify as additive manufacturing, in the sense that you are directly 3D printing the final production part that's going to go whatever on the airplane, on the car. You could probably count those applications in metals on like 2 hands and in polymers on 1 hand. So I'll get a little bit deeper into why that's true later. So just to kind of quickly overview, there's the 7 major categories of, or like classes of 3D printing. So the very first one is the one that Polyspectra is most relevant to, which is called vat photopolymerization. So there's a lot of different kind of brand names of this and variations on it. I tend to call this whole thing stereolithography. And here you have a liquid photopolymer resin that is sensitive to light, and basically wherever you shine light into it, which can either be from a laser or a projector, that liquid will cross-link into a solid material, and then you build the part up layer by layer. So the advantages of stereolithography or vat photopolymerization are the accuracy and like smoothness of the parts. So you can directly print things that have the same kind of finish and feel as an injection molded part. But then the disadvantages, well, traditionally, and this is sort of I'll get in setup, I guess, kind of the piece that we try to solve at Polyspectra is the material set that's available are very limited in terms of their ruggedness, durability, and I'll go a little bit more into that later. So one of the other things I just want to point out on this is in some of these other types of printing, it's possible to take a material that sort of has kind of an existing life or market in, let's say, injection molding, and then sort of like just figure out how to print that material, and whether or not it's the same quality is sort of another story. Whereas one of the challenges in stereolithography and vat photopolymerization is that there aren't really like analogs of these resins, or at least there aren't usually analogs of the resins out there that have an existing market. So new materials, you really have to kind of build a brand around the new material, which is a big part of our strategy that I'll explain later. So, all right, so quickly kind of go through some of the other ones, and not spend too much time nerding out on this stuff, which I could do for hours. So powder bed fusion is this idea that you're sintering nanoparticles together or melting nanoparticles together using a high energy laser source. So selective laser sintering is one form of this, but there are a number of different types of this, both in plastics, where you take kind of micron size plastic particles, and then also in metals and ceramics, and actually sand printing in this way is used all the time in forging complex metal parts in metal foundries. So this one is pretty versatile in terms of the types of materials that are relevant, because you're basically just taking an existing material, turning it into a very small particle, and then kind of fusing it together layer by layer. Binder jetting is, I guess, similar to the powder bed fusion, except instead of sintering it together, you're gluing it together. So the way of thinking about it is it's kind of like this powder bed, where you have a bed of solid particles that's getting, so up here, I don't know if you can see my mouse, but they're trying to depict this little roller on the top, where they're rolling out a thin layer of particles between every layer. But here, instead of like sintering them together or melting them together, you're basically gluing them together. So what binder jetting means is like glue jetting. So you have basically a inkjet type head that's shooting glue and also pigments and coloring. So you can do, if you want to, I don't know if you've seen the things in the mall where you like get yourself 3D scanned and then they print you like a little, I don't know, groom on a wedding cake with it's your actual face. Or Cyclotron Road made us like these action figures for us, where they like, took pictures of our head and then printed little custom action figures, where you do full color printing. That's done with binder jetting. Then sort of one over on the spectrum is like material jetting. So this one is kind of like combining the binder jetting with the photopolymerization. So you're using an industrial inkjet head to set the shape of the material. And one of the advantages of this is you can actually deposit. So in the same way that you have like a full color inkjet printer, you could have many sort of materials as the colors, and it could actually be color, or it could just be a different like stiffness or class of material. So you're using the industrial inkjet head, the jetting, to set the shape, and then you're following that with light to cure. And then there's also one that's called like sheet lamination. I won't spend too much time on this. It's not that exciting. It basically just stack sheets over and over again and like sinter them together, laminate them together. Then one of the last two, which are kind of important, so extrusion, so FFF or FDM are the two kind of acronyms for this. And this is probably like the most sort of has the highest level of kind of consumer awareness type of 3D printing. So these tend to be the cheapest printers that are out there. Like MakerBot was an example of this type of printing, where they sort of or the low end version of this. So if your kids are 3D printing in school, it's probably with this extrusion base. The advantage of this is that you can make a filament form of an existing thermoplastic that people already know and like. The disadvantage is that the part will never actually have the same properties that it would have if you molded it. And so not only are the properties of the material anisotropic, which means that the strength in the plane of the build surface versus out of the plane of the build surface is very different, like by a factor of 2 or more. So people call that like the Z strength issue. But then also the properties can be path dependent. So for a lot of regulated applications like aerospace or automotive or medical devices, this is like a really tough sell, because every single shape can give you like a different property. So you basically need to do your quality control isn't just about like which printer, which settings, which material. It's like, and also what shape and exactly what path did the build head raster. So it's a real nightmare to qualify. And then the last one is like directed energy deposition. So this is kind of just like 3D welding is the way to think about it. And this can be really useful for certain types of metal printing, especially what people call like near net shape printing. So you print something that's kind of clunky and has low resolution and ugly, and then you do a bunch of CNC finishing to it to get to the final part, but the speed and cost make it worth it. Okay, so I'm gonna kind of try to go quickly through the rest. Just so quickly, like I want to talk a little bit about like the playbook for additive and where it's won. So probably the most successful playbook has been what people call rapid tooling. And this is where like actually the industry as a whole, it's like kind of evolved from calling it rapid prototyping because they knew they weren't making functional parts, to then what people call rapid tooling, which is you print the mold for the thing that you want to make. And then additive manufacturing, like back in the 90s, people were like, well, you can't call it that because you're not actually making that. But now it's sort of come to encompass all of these things. So anyway, so the best example of rapid tooling is Invisalign. So they scan your mouth to get the shape of your teeth. They use computer software to figure out how they want those teeth to move to come up with a plan. And then what they 3D print is a mold that looks like your teeth. And then they thermoform the Invisalign retainer or the aligner over that mold. And then they use a robot to like clean up the edges. And so that the molded part is what goes in your mouth. So it's the biggest application for the stereolithography 3D printing by market size, but it's not actually printing the final part that goes in your mouth. And I guess tied to that, so this like idea of mass, so none of these playbooks are sort of like independent, like you can kind of have multiple of them play together. So mass individualization would be like this idea of the market of one. So dental is a very big market for polymer 3D printing because, unlike shoes where you can say, all right, you're a size 10 and it more or less fits. You can't really say your size 10 mouth, because that would be a pretty painful experience. So it kind of, the biological kind of uniqueness of your mouth kind of makes it make sense to use 3D printing for this sort of market of one thing. Third one is basically spare parts, and you could argue like all three of these kind of connect together in dental. So Chuck Hull, who's the CTO of 3D Systems and the inventor of stereolithography 3D printing, his joke is that dental is the world's largest spare parts business, because everyone's got, what is it, 32, something like that, teeth, and I think it's less than that. Anyways, don't quiz me on how many teeth I have, or I'm gonna get distracted. And then you lose them all the time. So that's that's like a couple billion teeth in terms of market size. Anyways, that's Chuck's joke. So obviously there are things in like a lot of the early wins in metal additive were from the Air Force, where they were flying B-52s that were made in 1962. The company that contracted to make that doesn't exist anymore. They don't have any way of manufacturing spare parts when something breaks. So there are a lot of examples where maybe the first version of it isn't printed, but then you print the spare part as necessary. And then process consolidation is a really important one. So people all the time will say, oh, well, like look at printing versus molding. Like injection molding is so cheap. As soon as you have the mold, it's basically free to cycle through. The plastic costs pennies. It's nothing. But where a lot of the big wins are in additive is you can print something that would have been 10 different molded parts that all not only need to get molded, but then also need to get assembled. And so that's the best example of that is the GE LEAP nozzle, which is like a fuel injection nozzle for their latest aircraft turbine. And they saved themselves something like $5 billion by metal 3D printing this part. So instead of it being like a couple hundred parts that needed to be assembled and welded and inspected, they got it down to like maybe, I don't know, I think it was like 10 parts. So they reduced the part count by an order of magnitude. And that's where even at production scale, additive could start to win. Then there's a lot of this idea around like just-in-time manufacturing or like inventory-free logistics. So one word for this is like the virtual warehouse. So UPS has actually made a couple of investments in 3D printing service companies because they actually store a lot of spare parts and inventory for large corporations. And then finally, like the one that sort of gets a lot of the visual attention, but there aren't really that many examples in production of it, is a use case where you can print some impossible geometry that would not be able to be made any other way, that gives you higher performance. So aerospace is probably the only space where this is true. The challenge here is that you really have to completely re-educate all of the engineers and designers around how to design for additive. All right, so I'm going to try to kind of move a little bit more quickly for this. So this is from like a Stratasys webinar. I just really want to point out that like a lot of the main customer issues are centered around materials. So like you can see in this, the only thing that's higher than the materials are not suitable is I don't use 3D printing, which I would interpret as like, well, maybe you would use it if the materials are suitable. And then also, this question is like, so the first question was like, what's keeping you from using printing? The second one is what advantage could you have by printing? And it's like, well, we need more cost-effective ways to make, products, right? So if you don't have materials that are strong enough to make your product, you're not going to do it. And new ways of manufacturing differentiated products, again, that's like bottlenecked by the materials. So the sort of summary, at least in the polymer 3D printing space today, is the hardware is there, the software is there, but there really are not production grade materials. So what that means is you're making molds, you're making prototypes, you're doing rapid tooling, but you're not directly additively manufacturing end-use parts. And my sort of summary, at least in the class of materials that we work on, just to drive home like how low the bar is, like how bad the existing materials are, is a disposable plastic spoon that you are going to throw out, so you don't think of that as like a high performance material, yeah, that is better than basically anything that you can 3D print today. And in terms of the temperatures that it can withstand, the tensile strength, the impact strength, the surface finish, the quality, all of these things. Okay, so that kind of sets up where we're trying to play with polyspectra. So really, I don't really think about what we're trying to do as being trying to get market share within additive manufacturing. I think of it as trying to unlock like a completely new total addressable market for additive manufacturing. So it's like growing the pie. And so where we kind of think about market size is against injection molded polymers. So that's about a $300 billion market globally. About 100 billion of that is for packaging and like, consumables and stuff. So we'll just assume like we're not, I mean, we could potentially print packaging, but like for the purposes of kind of where we're focused right now, we're focused on durable goods. So just the durable goods is about $200 billion a year market. And then if you just pick even like one kind of classic thermoplastic, so ABS plastic, that's Lego plastic. It's in, I don't know, all kinds of like outdoor furniture, consumer electronics, etc. Just that one polymer, which from a properties perspective is about, we're in some ways we're actually better than ABS, but we're about there in terms of the class of material. That's just ABS alone is a $50 billion market. And then this number at the bottom, honestly, it would be generous to say that this 3D printing photopolymers today is 2 billion. It's somewhere between 1 and 2, kind of depending on sort of how you count all the different types of printing. So our vision is really like, first and foremost, I mentioned before in stereolithography, because you're like, these resins don't have existing analogs, so you're not just saying like, oh, I'm printing ABS, like, don't you like ABS already? It's really important to build like a brand around the material. And so our sort of family of materials we call cyclic olefin resin, so that's core for short. And the playbook here is really to make this like the premier brand of polymer for additive manufacturing. So like shorthanding that as the Gore-Tex of additive manufacturing. And so if we're successful in making this direct additive manufacturing kind of come true, like so directly printing durable goods, then basically we'll have dramatically lowered the barrier to entry and cost of innovating in kind of physical products in durable goods. So instead of paying $100,000 for an injection mold, you can just have this kind of elastic capability to print what you want in the shape that you want it in one step. And so then in terms of kind of a medium term vision, the obvious thing in my mind to do with that is take it further downstream. So like 3M to me is probably one of the most inspiring companies in the sense that they take like fundamental chemical discoveries and material science and take that in some markets all the way to the Post-it notes and both the small Post-it notes and the extra large Post-it note that you can see on the wall behind me, or whatever, dental products for ceramics. They're about, in every iPhone there's like about 30 different films in there that 3M sells. They just are so impressive. And so I kind of call this like the 3M of 3D printing, which is like, if so now with this production additive manufacturing capability, what do you go do with that? You start to build like your own products in certain verticals where the sort of learnings that you have and the unique set of materials that you have gives you this completely differentiated playbook. And then the sort of longer term time horizon, I have this idea that I call the anything store. So obviously Amazon is the everything store. They've been successful. I think, maybe you can't buy quite everything yet, but you could basically say they did it, they won. So what the difference between anything and everything is that anything to me is for things that don't exist yet. So it's this idea of like, okay, I just designed a product and I want to like upload that to the cloud and have, it on my doorstep 2 days later. So like Amazon Prime for things that you just invented. And so that really is only possible once you have, one, production grade additive manufacturing, but two, this kind of completely distributed like network of digital manufacturing, which is sort of where things are trending. So I kind of, sometimes I'll call this like AWS for manufacturing, right? So you need the distributed compute power, right? In this case, like distributed print power, for that to even start to be relevant. And one thing that's important about this is like, I'm not necessarily saying like I'm going to own and operate all this stuff. I actually don't think that makes sense. So for the everything store for Amazon, it makes sense. They need to own and operate all the logistics, all the warehousing to get it to the customer fast enough. But in this case, the true bottleneck of this idea of the anything store is materials, right? So at the end of the day, you have to have materials to produce the parts. And so it's like, it doesn't matter if we're the ones owning and operating the printer. If we have the best materials, those are going to be the sort of bottleneck to like creating the physical products. Okay, I'm a little bit slower than I want to be, so I'm going to move quickly. So the bottom line is we're trying to, in this kind of next couple years with the funding that we just got from prime movers, focus on building the premier brand for polymer additive. So I mentioned already this like cyclic olefin resin, that's kind of like the family of materials. The yellow shading on this chart is like all the properties that we could hit. And then this dot in the middle, core alpha, is specs that we chose based on a couple of years of customer discovery in this space, to be able. So here we're showing the ability to do tough and hot at the same time, which nobody else can do. But what also comes with that is, durability, weathering, chemical resistance, impact strength. And so these are the things that you need to actually start printing car parts, airplane parts, electronics enclosures, medical devices, etc. This is just the first one. We have, this ability to tune the platform to a number of different directions. So these are kind of different areas that we're currently exploring taking. So this is kind of the roadmap for products down the line. So core impact is like pretty similar to core alpha, except that we're going to kind of emphasize impact strength and make it black. It's amazing how many people are like, this is amazing, I just need to be black. Then on the other side, we have a ton of people who are like, this is amazing, I need to be clear. So as I mentioned, dental is a major market for polymer 3D printing, and we have projects ongoing to do direct printing of dentures as well as aligners. I also mentioned before this idea of like rapid tooling, which has been around for almost 30 years. And it was kind of surprising to me, because it's been around that long, that people were still really disappointed with the materials that were available there. And it is sort of an existing market. People know what to do with it. So we're working on something for making tooling for injection molding cavities that can last longer. So the problem with the materials today is you can do it, but like after maybe 5 shots in the molder, the mold falls apart and you got to print a new one. So it's not very cost effective. And then we're also supported by SBAR from the National Science Foundation to work towards very intricate and complex 3D printing of like biologically inert materials for medical devices. So I mentioned before, like there's like with this, in this idea of the like 3M of 3D printing, there's a ton of different ways that we could play it. And so obviously the focus for us right now is on building that brand of resin. So we do not make the 3D printer. There are a ton of people that make very good printers that are very hungry to get better materials. And we have a number of partnerships already in place to sort of sell our resin through those channel partners. So the focus channel for us is really on being like the best material for this stereolithography 3D printing. And we have partnerships with a number of folks, including Origin and 3D Systems there. And then on the sort of upstream side, like one of the extremes is we're like co-creating the product with our customer. So they're these are companies where they might have some material IP that they want to bring to the equation. So for example, Dentsply, like they know exactly what the material for a denture needs to be, and like the pigment to get it the right color, pink for your mouth, etc. And so we're willing to sort of work with end users to kind of build like a developer's kit for a material where we're kind of co-creating the final solution with them. And then all the way kind of on the other end of the spectrum, we're not going to be doing too much in this, like with the current funding that we have on like trying to go direct to our own products. But there are some applications where we will just focus on selling the parts, especially like smaller and more intricate things in like the medical device and diagnostics space. A few drops of resin is only worth pennies, but if you print that into this really intricate tiny thing, that could be worth like thousands of dollars. So it kind of doesn't, and some of these smaller things, it doesn't make any sense to sell the resin. In terms of the growth engine, like obviously we picked a really hard problem to go after, and we kind of co-create that solution with partners and customers. And then the recurring piece of the revenue is kind of the resin sales. So if you can get a new material qualified, that's very sticky. So like people still call it Teflon, they don't call it polytetrafluoroethylene. People in 3D printing, they ask all the time, Ultem, how do I get Ultem? And this is just like the first pretty good material that Stratasys commercialized in the 90s. People are still 20 years later, like, how does it compare to Ultem? So it's very sticky. And then obviously like the flywheel piece is the more times we do that, the bigger the catalog we have, the more channel partners that we have, the more verticals we can go into, and the cheaper it is for us to kind of iterate on new products. Last slide, and then I'll show an outdated picture of our team, but there's a ton of different. So I think the key thing through this loop is like we're aggregating all the IP from those learnings in every application. So like everything that I do for dentures helps me do aligners faster. Everything that I do in dental helps me with all the data that I need to do medical. So that would just be like some examples. So there's obviously some kind of core chemistry on the photocatalyst side that we will not be licensing to anybody. We have a lot of patents on that stuff, but we also have a lot of trade secrets around like what our favorite structure of catalyst is, or certain like additives that are in very small quantities in the resin, but that improve the performance in a huge way. And then there's sort of the monomers, which is like what is this material ultimately going to be made of? And in some cases, like that might be a collaborative discussion with a partner that we're really tight with. Then additives, things like what color is it going to be? Do you need to sort of modify the surface or put something in there? Again, that there's potential for co-creation there. And then finally, the like print process and settings. There's an amazing number of variables to running a successful 3D print that, obviously that needs to be part of the collaboration. So, there are teams of people at 3D Systems, for example, that just focus on the print settings and do nothing but that all day, every day. So obviously they have a lot of experience in that. So we are around 12 people now. This is an outdated picture, but yeah, we've added 3 people since closing this round, and have one that's about to start in a couple of weeks, and another offer that we're about to make. So we're kind of growing quickly, and in case we didn't catch at the beginning, we're based in Berkeley, California. So if you're ever in the East Bay, I'd be happy to host you and say hello in person.